Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the heating effect of current, electric power and its units. This topic is meant for class 12 students of CBSE, ISC and different state boards. This topic will also be found useful for different competitive exams like NEET and JEE Mains. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Heating effect of electric current. When a source of EMF is connected across the free ends of a conductor, a potential difference is set up across its ends. This potential difference accelerates the free electrons in the conductor. As they move, the electrons collide with the positive ions and lose some of their energy to the positive ions. This increases the internal energy of the conductor and its temperature rises. In other words, when a current flows through a conductor, a part of the electrical energy is converted into heat. This is known as the heating effect of current. The amount of heat produced in a conductor carrying a current is equal to the work done against the resistance of the conductor. This energy is given off to the surrounding by the conductor. Amount of heat produced. Let a potential difference V be established across a conductor AB of resistance R. If current I flows through the conductor for a time t, then the charge that flows through the conductor in time t is Q equal to IT. When the charge Q flows from one end of the conductor to the other end under the influence of a potential difference V, the amount of work done by the electric field is W. This is given by the product of charge into the potential difference. So for Q, we put here I into T, and this is V here. So this is IT into V. But from Ohm's law, we have V equal to IR. So equation 1 can be written as W equal to IT into IR. So this is I square RT. Okay. This work done appears as heat. Hence, heat given out by a conductor of resistance R when a current I flows through it for a time t is given by U equal to H equal to I square RT. Here, U is the energy released, H is the heat produced. Because heat is a form of energy, we write energy equal to heat produced, and that is equal to I square RT. Okay. This relation was established by Joule, and hence this phenomena is known as Joule heating. Clear? The following points can be drawn from this relation. First, as H is proportional to I square, the relation holds for both direct as well as alternating currents. That is why electrical appliances such as heaters, toasters, geysers, filament bulbs work equally well on both AC and DC. Second point, as H proportional to I square, reversing the direction of current does not change the amount of heat produced. Joule heating is therefore irreversible. So let us see an example. A current of 5 ampere flows through an electric heater operating at 220 volt. Find the amount of heat produced in 5 minutes. Okay. So the amount of heat produced is given by W equal to VIT. Put the value of I equal to 5 ampere, V equal to 220 volt, T is 5 minutes, and this is equal to 300 second. Put the value in the expression for W. So W is equal to H equal to VIT. V is 220 volt, I is 5 ampere, and time T is 300 second. So if you multiply 220 volt into 5 ampere into 300 second, it comes out to be 330,000 joule, and this is equal to 3.3 into 10 to the power 5 joule. Okay. Electric power. The rate at which the electrical energy is dissipated or consumed in an electric circuit is known as electric power. If H be the energy dissipated in time t, then electric power is defined as the ratio of H and T. So P is equal to H upon T. H is equal to I square RT. So this is I square RT upon T. So P is equal to I square R. Okay. But from Ohm's law, we have V equal to IR. Hence, P can be written as IR into I. This is V into I. V for I, we put V upon R. So this is also equal to V square by R. Okay. The following conclusions may be drawn from these equations. First, when the resistors are connected in series, then P proportional to R and P proportional to V, as I is a constant. In other words, the larger the resistance, greater is the power consumed. Also, greater is the potential difference across a resistor, greater is the power consumed. Second case, when the resistors are connected in parallel, we have P equal to V square by R. We have seen this equation. P equal to V square by R. So, P proportional to 1 upon R as V is a constant. In other words, smaller the resistance, more will be the power consumed. Third, as P equal to V square by R, if V is constant and the resistance is changed to R by N, then the power consumed will be P dash equal to V square by R upon N. So this is N times V square by R. And since V square by R is P, this is N times P. Okay? Thus, if the resistance is decreased by a factor of N, the power consumed will increase by the same factor N. Next, if N resistors, each of value R, are connected in series and a voltage V is applied across this combination, then the power consumed will be PS is V square by NR. N resistances of equal value R are connected in series, so their equivalent resistance is N times R. And since P is equal to V square by R, and here R is equal to N times R, so PS is V square by NR. Instead, if N equal resistors are connected in parallel, then PP is equal to V square by R upon N. This is the equivalent resistance of N resistors of equal value R in parallel. So this is N times V square by R. So we have PP upon PS is N V square by R upon V square by N into R. This is equal to N square, or PP is N square into PS. So in other words, the power consumed by N equal resistors in parallel is N square times the power consumed when the same resistors are connected in series, provided the voltage across the combination in both the cases remains the same. Next, an electrical appliance consumes the stated power P only if it runs on the specified voltage Vs. If the applied voltage Va is more than the specified voltage, the appliance will get damaged due to the current exceeding its rated value. If the applied voltage is less than the stated voltage, then the power consumed P dash will be Va square by R. This is Va square upon Vs square upon P. This is from this relationship. We have P equal to Vs square by R. Okay. So stated voltage is Vs, the power is P. So P is equal to Vs square upon R. So this comes out to be Va upon Vs whole square into P. This means that the power consumed is less if the applied voltage is less than the specified voltage. Okay, VA is less than VS. So VA upon VS is less than 1, which means that VA upon VS, the square of this will be much less than 1. Okay, and therefore from equation 9, P dash is much less than P. Clear? So we say that the power consumed is less if the applied voltage is less than the specified voltage. And that's why the electricity boards intentionally reduce the voltage during peak hours to meet the energy requirement. Okay, so this is one important information for you. Next, the electric power is generated at the powerhouse and is transmitted to far off places by means of electrical network. If the power is to be carried over several kilometers, the cost of conductors employed to carry the electrical power from the place of its generation to the place where it is to be used, and also the power loss, that is I square R, is of prime importance. Power loss is the power lost as heat in the conductors. So what are the practical consideration? When an electric current flows through a wire, heat is produced. Therefore, while choosing a wire, we should keep in mind the purpose for which it is to be used. We list below some materials used for specific purposes. The first is the wire used for electrical connections and power transmission are generally made of copper and aluminum, as their resistivity is very small. Second is the fuse wire is made of an alloy of lead and tin, as its resistivity is very high and melting point is very low. So it can break the circuit if the current exceeds the rated value. Okay. Third, the standard resistors are made of materials such as nichrome, constantan, manganese, whose resistivity is quite high and temperature coefficient of resistivity is negligible. Next, the filament of an incandescent bulb is made of tungsten, as it has a very high melting point. Next, the heating element of electrical appliances such as electric iron, electric heater, immersion rods are made of nichrome, which has high resistivity and high melting point. Next, a fuse wire should have high resistivity and low melting point. Its melting point should be slightly above the temperature it is expected to attain when the maximum permissible current flows through it. It is generally made of an alloy of tin and lead, that is 37% lead and 63% tin. This is alloy. Okay. The fuse wire's melting point should be somewhat higher than the temperature it is expected to attain when the maximum permissible current flows through it. If this is not so, the fuse wire will melt and break the circuit. तो जितना टेम्परेचर हो सकता है करंट फ्लो होने से उस वायर में, जितना मैक्सिमम करंट फ्लो कर सकता है, और इस कारण से जितना भी टेम्परेचर बढ़ सकता है उससे थोड़ा ज़्यादा फ्यूज वायर का मेल्टिंग पॉइंट होना चाहिए. ओके, नाउ वी कम टू यूनिट्स ऑफ इलेक्ट्रिक पावर. The unit of energy in SI is joule and that of time is second. Since power is the energy dissipated or used per unit time, the SI unit of power is joule per second and is known as watt. So joule per second has a name watt. 1 watt is 1 joule by 1 second. So this is 1 joule per second. As P equal to Vi, The unit may also be expressed as volt into ampere, VA. Hence, 1 watt is 1 joule per second is 1 volt into 1 ampere. Energy consumption. आपने इनकैंडेसेंट बल्ब पर देखा होगा, लिखा रहता है 220 वोल्ट 100 वाट, या 220 वोल्ट 60 वाट, या 220 वोल्ट 40 वाट. दिस इज कॉल्ड द रेटिंग ऑफ द बल्ब. यदि बल्ब पर लिखा हुआ है 220 वोल्ट 100 वाट, इसका मतलब ये है दैट व्हेन दिस बल्ब इज ऑपरेटेड एट 220 वोल्ट, it will consume 100 watt of power or 100 joule of energy every second. Okay? उसी तरह से यदि लिखा हुआ है 220 वोल्ट 60 वाट, इसका मतलब if this bulb is operated at 220 volt, it will consume 60 watt of power and nothing else. The joule is a small unit. Therefore, for domestic and commercial purposes, a bigger unit called the kilowatt hour, kWh, is used. If an electrical appliance that consumes 1 kilowatt, that means 1000 watt, is used for 1 hour, the energy consumed is said to be 1 kilowatt hour. Thus, 1 kilowatt hour is 1000 watt into 1 hour. For 1 hour, we write 60 into 60 second. So this comes out to be 3.6 into 10 to the power 6 watt second. So this is 3.6 into 10 to the power 6 joule. The domestic consumption of electricity is measured in board of trade unit, BOT, or simply we call unit. 1 unit is equal to 1 kilowatt hour. Thus, 1 unit is 1 BOT is 1 kilowatt hour, and this is equal to 3.6 into 10 to the power 6 joule. If I consume 200 units of electricity, then the total energy consumed is how much? That will be equal to 200 units will be equal to 3.6 into 10 to the power 6 into 200 joule. Okay. Now, the power rating of a resistor. The power dissipated I square R in a resistor appears as heat in the resistor. यदि बहुत ज़्यादा हीट प्रोड्यूस हो जाए तो resistor may be damaged, but sometimes we require a large amount of heat to be produced in an appliance such as heater, geyser, or electric iron. Okay, so we make such appliances with materials that have a high resistivity and high melting point. The filament of an electric bulb, for example, is made of tungsten, which has a high melting point. The power rating of a resistor is the maximum power that it can handle without getting damaged. Table 1 lists some of the materials used in heating appliances along with their melting points and resistivities. So this is all about the heating effect of current, electric power, its unit, and the power rating of resistors. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.